Welcome to this explainer. Okay, picture this. You're cruising at 30,000 feet. It is a wildly hostile environment up there. Outside the cabin, it might be minus 50 degrees, but literally just feet away from where you're sitting, jet engines are burning fuel at thousands of degrees. To survive that, an aircraft has to act almost like a living, breathing organism. It comes fully equipped with its own hidden immune and nervous systems designed to detect and fight off threats. So today, we're going to explore the anatomy of these absolutely critical in-flight defenses and see exactly how they keep you safe. So here is our roadmap for today. We'll quickly cover understanding aircraft fires, move into the science of combustion, look at fire detection technologies, break down alarms and warning systems, and finish up with regulation and maintenance. Let's dive right into Section 1, Understanding Aircraft Fires, Defining the Threat in Aviation. You know, the whole purpose of fire protection systems isn't just some engineering afterthought. These are highly integrated, sophisticated measures built specifically to protect life and critical systems by stopping a catastrophic hazard before it spirals out of control. But the very first step is realizing that not all fires are created equal. Different environments on a plane require completely different approaches. We classify fires into 5 distinct types based on their fuel source. You've got Class A for solid materials like paper or wood, Class B for flammable liquids like aviation fuel, Class C for electrical fires, Class D for combustible metals, and Class K for cooking oils. Think about it. If a fire breaks out in a galley oven, that's a Class K fire, you absolutely cannot fight it the same way you tackle a Class C electrical fire down in the avionics bay right under your feet. If you use the wrong suppression method, like, say, spraying water on a massive electrical fire, that could be catastrophic. So knowing the exact class is the foundational step in defeating it. Moving right along to Section 2, the science of combustion, knowing the enemy. Before we even look at the aircraft's technological immune system, we really need to dissect the science of the pathogen itself, combustion. To start a fire from common ignition sources like an electrical arc or a hot surface, you need 3 specific elements working together. It's famously known as the fire triangle. Honestly, think of combustion like a 3-legged stool. You absolutely must have oxygen, heat, and fuel to keep it standing. The whole concept here is that if an aircraft suppression system can knock out just one of those legs, like by flooding a sealed cargo bay with halon gas to completely push out the oxygen, well, the fire instantly collapses. But here's where it gets really interesting. Modern chemical suppression requires a much deeper understanding than just that basic triangle. Science actually expands that original model into the much more complex fire tetrahedron, and it does this by adding a 4th, totally crucial element, the uninhibited chemical chain reaction that actually sustains the combustion and lets the flames spread. This updated model is so important because modern chemical suppressants don't just cool the area down or smother the fire, they literally interrupt the chemical reaction at a microscopic molecular level. At that molecular level, we're talking about an exothermic reaction, meaning it is aggressively releasing energy into the environment. Fuel molecules are rapidly combining with an oxidant, like the oxygen swirling around in the cabin air, to yield carbon dioxide, water, and intense heat. This rapid chemical process just accelerates molecular activity exponentially, and that generates the severe heat, the open flames, and the blinding smoke that our aircraft systems are specifically designed to counteract. So, knowing all that underlying chemistry, it begs a pretty wild question. How in the world does an airplane actually smell or sense these microscopic combustion byproducts in a sealed cargo compartment, miles above the ground, while blasting through the air at hundreds of miles per hour? Which brings us perfectly to Section 3, Fire Detection Technologies, the aircraft's nervous system. Think of this as the aircraft's sensory nervous system. It uses highly specialized detectors designed to take a beating from extreme vibration and heat, all while providing critical early warnings to the flight deck. When we're talking about smoke, aviation engineers have to carefully weigh the pros and cons of different tech. On one hand, you have optical smoke detectors. These are incredibly reliable for massive spaces, like cargo bays and avionics compartments, because they're great at detecting visible smoke early on. On the flip side, we have ionization smoke detectors. Now, these are highly sensitive to invisible combustion particles, but the major trade-off? They can be incredibly vulnerable to false alarms if they get contaminated by just a bit of dust or condensation. And look, a false alarm from a dusty ionization detector means an emergency landing, deploying oxygen masks, and ruining the travel plans of hundreds of passengers. That is exactly why engineers have to choose the exact right sensor for the exact right space.
Now, for heat and actual flames, the approach completely shifts. Infrared or IR flame detectors offer lightning-fast response times, but they require a direct, unobstructed line of sight to the fire. Contrast that with continuous loop thermal switches. I want you to imagine the environment inside a massive jet engine for a second. It is deafening, it's vibrating violently, and it's already incredibly hot. Delicate optical sensors? Yeah, they wouldn't last a single minute in there. That's why engineers use these continuous loop thermal switches. They literally wrap around the engine like a highly sensitive, heat-resistant nervous system, stretching across large, brutal environments like engine nacelles and accessory bays. They are incredibly robust, built to survive where anything else would just quickly fail.
But, sensing the danger is really only the first step. Detecting the fire is only half the battle. The aircraft's systems have to instantly translate that microscopic smoke detection into an unavoidable, blaring warning for the humans actually flying the plane. And that takes us to Section 4, alarms and warning systems screaming for help.
Once a fire is detected, the aircraft has to alert the crew right away through a highly prioritized, centralized system. But here's the catch. When a sensor goes off in the belly of the plane, it doesn't just bypass everything and instantly ring a loud bell in the cockpit. Instead, that raw data hits a control and monitoring unit. Think of this unit like a digital bouncer. It actively processes the signal and applies strict warning logic based on that specific compartment's hazard level to verify if the threat is real. Only if the system absolutely confirms the danger does it trigger the master warning, deploying immediate visual and oral alerts. That microsecond delay in logical verification is vital. It prevents pilots from overreacting to harmless electrical blips, ensuring they are only dealing with a verified, real-deal emergency.
These master warning systems are heavily influenced by human factors and the psychology of a crisis. Imagine a sudden emergency at 30,000 feet. A pilot's heart rate spikes and their cognitive load is instantly maxed out. They simply do not have time to read paragraphs of text on a screen. Because of that, systems utilize specific color coding standards, like a bright, flashing red master warning that instantly cuts through the chaos, paired with redundant visual and audio alarms. It is a brilliant fail-safe design. It's built specifically to ensure the crew is immediately aware of the danger, capturing their full attention without paralyzing them with overwhelming or confusing feedback.
Finally, let's look at Section 5, Regulation and Maintenance, keeping the system reliable.
Let's be real for a second. Absolutely none of this amazing, advanced technology matters if it isn't rigorously maintained and governed by strict engineering standards. It has to be perfectly reliable. Aviation authorities like the FAA and EASA, they don't just suggest safety guidelines, they mandate them down to the literal millisecond. Regulations demand precise maximum response times. That means a system has to detect a fire within a strictly defined number of seconds, with zero room for error. None. They outline uncompromising equipment limits, extensive redundancy requirements, and safety management standards to guarantee total reliability across every single fire protection installation on that aircraft. To actually meet those insanely demanding regulations, maintenance has to be a constant, ongoing effort. And this is where aviation technicians really become the unsung heroes of the skies. It's an endless, meticulous battle to keep these systems flawless. They aren't just changing oil and kicking the tires out there. They are performing routine testing of continuous loops, carefully verifying correct orientation and microscopic spacing during installation, and protecting those delicate sensors from mechanical damage and intense engine vibration. Crucially, they have to keep the detectors meticulously clean to prevent those dangerous false alarms we talked about earlier. It is all about strict compliance with manuals and regional guidelines, ensuring that the invisible safety net is absolutely perfect for your next flight. So, I want to leave you with this final thought to ponder. As aircraft become increasingly reliant on complex electronics, massive battery banks, and higher energy systems, how will these safeguards evolve? Will the next generation of aviation fire protection rely more on AI and advanced sensors to predict fires before they even ignite, rather than just reacting to the smoke and heat after the fact? It's a fascinating glimpse into the future of proactive safety at 30,000 feet. Thank you so much for joining me on this explainer.